So with that, I'll open up the floor to all of you.
Perfect. So would you mind going over how to find a limit of a sequence real quick?
Sure. Do you have an example you want to look at, or should I just?
Yes, directly from the textbook. Number 51A.
So this, you said from the textbook. So this is from that sheet on Canvas that
Yep.
Mark posted?
I know it's probably pretty easy, but I just want to confirm what the process is.
All right, Mark, I just want to make sure. So you're talking about the file, that image that was on Canvas, right?
Yeah.
Okay, cool. And you said 51?
51A.
51A, okay.
And maybe B if you can.
Yeah, not a problem. So 51. Okay, so let me log into this meeting with my iPad so I can take some notes. Also, the notes I take for today, I intend to share with everyone. So if I forget to send those out, you're welcome to remind me. All right, so number 51. Mark, why don't you go ahead and read me what that sequence is?
Negative 45 to the power of K.
Okay, so basically we're trying to find the limit of this, right?
Yeah.
All right, so the limit as K goes to infinity of -4/5 to the K. So let me open this up to everybody here. What kind of sequence am I looking at?
Geometric.
Geometric.
That's geometric, right? So we're looking at a geometric sequence. So we have a pretty simple condition to determine whether or not those converge. So what's the condition for a geometric sequence or a geometric series to determine whether it converges?
R has to be between -1 and 1.
Right, so you've seen this look a couple different ways. That rate of change is between -1 and 1, or you might have seen this. Absolute value of the rate is less than 1.
And the only wrinkle in this is that between sequence and series is that a series and a sequence will converge if it's one. The sequence will the -1 boundary case is different between the two of them, if I remember right.
That's correct. But we do not have to worry about that here. So, and I think 51A is just asking about whether the sequence converges, right? Is that correct, or am I looking at the series for 51A?
Can you still hold that up in front of you, Mark?
See, 51A says, yeah, limited the sequence. So A is sequence, B is series. Okay, so based on what we've said about, we know this is a geometric sequence. We know what the rate is, or maybe do we know what the rate is?
I need to remember that formula. It's very short and simple. 1 minus R over A.
A over 1 minus R.
Almost.
Okay, so you're talking about that formula that you just said. Here's what I heard. I heard A over 1 minus R. What is that formula for? What does that represent?
Isn't it for a series?
Yeah, that's for a convergent geometric series, which is not yet what we're talking about. So hold that thought, because part B, we're going to get the sum of this series if it converges. But for determining whether or not the sequence converges, we don't need that yet. So you have all told me the only condition I need to worry about to determine whether a geometric sequence converges is its rate of change. So can we do we know the rate of change for this particular sequence?
Yes,
What is it?
-4/5.
Good. And that should be everything we need to know. Does this sequence converge then?
Yep.
Yes, it converges to 0.
All right, so not only do we know it converges, but Mark is saying that it converges to 0.
And basically, if it converges to 0, 0 is the limit.
That's exactly it.
Okay, that's what I thought. I just wanted to
Yep.
confirm what it meant, because the wording of the textbook just looked a little weird. It was a little bit different from what I remember from the homework.
Oh yeah, so let me throw a true or false at you before we move on to part B. True or false? If a geometric sequence converges, it converges to 0.
Not true, false.
Give me a
True.
counterexample.
Example is if a geometric series is a fraction or like a ratio, if the actually I need to look at my notes 1 moment.
Okay.
Isn't there a case where if it's 1, like r equals 1, then it's just 1?
Yeah, I guess you could say that. So like if you had 1 to the power of n. So that's a case where the sequence would converge. What would the series do?
Diverge.
Yeah, because so let's look at this silly example that we probably haven't thought much about. So this sequence right here, what is the limit as n grows of 1 to
1.
the power of n?
Never leaves.
Yeah, it's every term of that's going to be 1. But if instead I'm looking at this, the limit is n approaches infinity of this guy, what does this series do?
Goes to infinity.
Goes to infinity. And because I feel like you can never stress it enough, you're obviously on Friday going to have to determine many times whether a sequence converges or diverges. What is the first thing you should look at, when you're trying to make that determination?
If it's a common form,
I think there's something you can look at even further upstream than that.
You can take the limit, and if it's anything that's not 0, then you know immediately that it diverges.
That's absolutely right. So basically, if the limit of, and one more thing, D, you say take the limit. The limit of what? Let's be specific.
The limit of the sequence.
Right. If the limit of the sequence is anything other than 0, your series has no chance to converge. So that's the divergence test or divergence theorem, which I believe is like the first test that he introduced you to.
It goes the other way too, that if you have a series that converges, then the limit of the sequence has to be 0.
Absolutely. So yeah, and that's called a contrapositive. Basically, I'm not going to get too much into the generalities of that, but you're absolutely right. So the divergence theorem says if your sequence does not converge to 0, the series associated with it diverges. And yeah, the contrapositive says if the series converges, then the sequence must converge to 0.
So
All right,
if
so
we're asked to find if a sequence converges, if we instantly recognize it as something of a series that converges, then we already know that the sequence converges to 0.
right. So yeah, if you recognize a convergent series, the sequence converges to 0. All right, so
have a
A asks
question.
about the limit of the sequence. B is asking about this sum, essentially. So we have said this sequence converges to 0. For a geometric series, does that mean that we can say this series converges?
yes.
Yeah, for geometric series, you can say that. Yeah, if the sequence goes to 0, then the series converges to something. So how do I find, and now we can use this formula that you all threw at me just a bit ago. So how do we attack it here? How am I going to find that sum?
You need to pull out an n, so it becomes negative 4 over 5 to the n minus 1.
Okay, so I have a proposal for a rewrite here. So if we pull out a negative 4 to the 4/5 to 1, then that makes this negative 4/5 to the n minus 1. I had a question in the chat. I'm confused how we know the rate. Can someone answer that? How did we find this rate of negative 4 over 5?
I answered in the comments.
Okay. D says the denominator is larger than the numerator, so we know that the distance from 0 is less than 1. Jacob, I think what Jacob's asking, and correct me if I'm wrong, is how do we know specifically that the rate is negative 4 over 5?
Yeah.
Okay.
Oh, I mean, you just factored out the negative 4 over 5, multiplied it so that we have a exponent of n minus 1.
Right.
Oh, okay.
And I'm going to expound on that in a couple different ways. Alondra's asking, what test are we doing for B? So really, there's no test we're doing for B. We've actually already done the test. So we've already done enough work to know that this series converges. So what test did we do to realize that this series converges?
Divergence.
Remember, the divergence test cannot tell you.
The geometric series test that
Yeah,
says that
geometric
if it-
series. And one more note about the divergence test. The divergence test will never tell you that a series converges. It either tells you that a series diverges, or it tells you no conclusion at all. So be careful with that one. All right, so now that we have written this series like this, we have negative 4/5 times negative 4/5 to the n minus 1. Can I go to the formula with that?
You need to pull that out in front of the sigma. The first negative 4/5 to the one that we pulled out.
Yeah, I can. Do I need to do that?
Oh, you don't need to. You
No.
could just treat that as your A.
Yeah. And there's one thing I want to go out. Let's do the formula first, and then there's one more thing that I want to talk about with geometric series that I think is hanging people up. So what do I use for my value of A here?
And what one other I could be confusing myself. Do we need to rewrite this to index it from n equals 0, or does it work with n equals 1?
The short answer to that I'll give is that it doesn't matter.
Okay.
Really, all that matters is let's really unpack this formula. What does A represent in this formula?
Isn't it a constant?
It is a constant, but where do I get that constant from?
The rate of change.
No, the A is not the rate of change. That's what R is. A is the first term in the sequence. So my first term in the sequence is going to be what?
Negative 4 over 5.
Negative 4 over 5 over 1 minus, what's the rate?
Negative 4 over 5.
Negative 4 over 5. So I get negative 4 over 5 divided by 9 over 5. So we get a sum of negative 4 over 9. Okay, before I elaborate on this a little more, are we okay with this sum?
Yes.
Okay. One thing I'm a little concerned about is, I think there's a lot of effort made on, getting a geometric series or geometric series to look like this. You have some first term A times some rate to the n minus 1. And there's a lot of you know, it seems like there's a lot of pressure to get us into this form here. So one thing I want to point out just fundamentally is that this formula here, the sum to infinity of a geometric series is equal to a over 1 minus r. And all you really need to focus on is what's the first term and what's the ratio or the rate of change, however we're going to look at it. So let's go back to how this series is written originally. I think if you need to, it's never a bad idea. I mean, and it doesn't take that long to just figure out what the first few terms look like. So start plugging in values at n. And this is Ben. This is why I say it doesn't really matter where your series is indexed from, because the first term is the first term. Just make sure you're obeying, you know, the expression and what the index is. So when n is equal to 1, I'm going to get -4/5. When n is equal to 2, I'm going to get plus 16 over 25. And then minus 64 over 125. And then I'll do one more. 256 over 625.
Close enough.
I believe that's correct. Okay.
I-
And then this is going to continue forever. So if you do something like this, then I think it makes it more obvious what the first term is and what the ratio is. I mean, certainly now that I've written out some terms, I know that this right here is A. And let's say this. Let's say I've gotten this far without figuring out what R is equal to. If I realize I'm looking at a geometric sequence, what's another way I can figure out what that value of R is?
Ratio test.
I don't even need anything that complicated.
Does the one term compare the one term against the other?
Right.
Yeah.
Yeah, so I know that basically you can pick any terms that are back to back. I know that 16 over 25 times some R is equal to -64 over 125. And you can either take my word for it or you can calculate this yourself, but you should get -4 over 5 for R.
So it's just the multiplier?
Yeah, that's all R is. Yeah, the rate of change. In the past, when I've taught this, I use the term common ratio because that's a constant that you will always multiply that by one term to get the next one. That's what makes a geometric series a geometric series. But I'm sorry, what was that?
Just said I really like that explanation.
Good. Yeah, I think I just think it's a little counterproductive to get so focused on making your expression look like this when all you really need is, you know, by whatever way it makes sense to you to figure out what the first term is and what the common ratio is.
And that also helps make more sense of what the A over 1 minus R is. You know, first
Yeah.
term over 1 minus the ratio.
Good. All right. So that was 51. Who wants to go next? Or I can pick something.
I have a more general question.
Sure.
So I forget which iMath it was, but a while back we had to derive a sequence. And, you know, for some of them, like if it's like 1 over 1, 1 over 2, 1 over 3, those are easy.
Right.
But do you know any like tips or kind of recommendations for more complicated sequences? Or is that even going to be?
That's definitely going to be something you'll have to do. I don't want to. I'm not sure how complex you'll have to look at. But I think this is one of those things that it's unfortunately hard for me to answer because it all comes down to recognizing patterns. I'm actually going to look at this sheet from the textbook, see if there's a good one on here that I can. None of these go that direction.
Yeah, because it's almost like, I don't want to call it a scale, but it's a little bit like that, where it just,
Yeah, I mean, it's one of those things that I mean, it's possible that it just jumps out at you, but you absolutely, I mean, there are some systematic approaches you can finding and Rodolfo's asking for a ratio test example, which I think is a good one to look at. All right, here's one that I found on the internet. So 0, 1, 3, 6, 10. That's as far as it goes, but I'll continue a little more. 15, 21. All right. So this might not be as complicated as what you were looking at, but there's a few things we can look at here. So what are the really easy things we can look for? Like we just looked at a geometric sequence. Is there any chance this is a geometric sequence?
No.
Nope. All right. What else do we notice, if anything, about the way these terms are arranged?
It's plus, it's like 2n plus 1.
2n plus 1? Let's try that. If you have a hypothesis, let's test it. So, you know, let's put this in a table form. And one thing I can always suggest is, you know, organize whatever you're given that might make something jump out at you. How many terms do I have here? 1, 2, 3, 4, 5, 7. All right, does 2n plus 1 work?
No.
Okay. So 2 times, yeah, that one I think you're gonna, so if 2n plus 1, you know, no, I've told you before that sequences are not really functions, or they're not continuous functions. But what kind of function is this right here?
Would it be a factorial at all?
The one that I'm looking at,
Or
or are you
linear?
giving me
Or the linear?
yeah, this is
Talking about
linear,
the
right?
example I gave?
But so you gave me a linear function. Is this sequence linear?
If it would be linear, then it would have a rate of change, right?
It would have, yeah, it would have like an additive rate of change. So in a geometric series, you can multiply by one term a constant ratio to get to the next. I don't think Mark used this term, but you know, a linear function, you can think of that in terms of sequences as an arithmetic sequence, where there's a constant
I
difference
think,
adding to each time.
yeah, I think I'm seeing the pattern in this one.
Okay, what pattern are you seeing?
So it keeps adding an extra value. So it goes +1, then +2, then +3,
Right.
then +4, then +5.
And remember, this is one of the things that Mark encouraged you to look for is, so we pretty easily saw that the rate of change between terms was not constant, either multiplicatively or additively. So one thing we can look at is, you know, go 1 degree deeper. What are the rates of changes of the rates of changes? So now look at this new sequence, 1, 2, 3, 4, 5, 6. Does that look a little more digestible?
Yes.
Right. So yeah, clearly, I mean, these, I am just adding 1 each time, right? So here's what I know. The rate of change of the rate of change of this sequence is constant. Do you remember what kind of sequence I'm looking at there?
So would this be parabolic?
Parabolic, yeah. So
Quadratic.
yeah, parabolic. Yeah, I mean, you're talking about the same thing. What kind of graph am I looking at versus what kind of function? But basically, we're looking at a quadratic. So one thing I would like to do, I'm going to make some more room here. We realize this is going to be a quadratic. So because of that, it's worth my while to make a new row to this table called n squared. Because I know that my sequence is going to have some n squared component to it. So 1, 4, 9, 16, 25, 36, 49.
Can take the difference of them and can divide the one by the other to see if another pattern pops out.
I think we actually are going to have everything we need here. So basically, you're going to have something that's like this: blank n squared plus blank n plus some constant. Because if we've said this is a quadratic, that's what quadratics look like, right?
Yeah.
3 terms. I have a n squared, n, and a constant. So basically what we're doing here is filling in the blanks.
Can't be more than 1n squared because, can it be more than 1n squared? I don't think it can be more than 1n squared.
N and C would have to be negative, right?
What's that?
Because the first term is 1, or one of them would have to be negative.
I'm not sure about that yet.
Is it just n squared minus n?
Let's try that. Let's try a sub n equals n squared minus n. So then let's make a new table or a new sequence based on that. 1 squared minus 1 is 0. 2 squared minus 2 is 2. 3 squared minus 3 is 6. 4 squared minus 4 is 12. So I do not think it is n squared minus n, but I think that we're extremely close.
Yeah, because those are just twice what we want, right?
Exactly. So what am I going to do to repair this thing?
Divide the whole n squared by n over 2.
Yep. So yeah, 1/2 times n squared minus n. That I would trust. And
Awesome.
yeah, so I think of all the different sequences you've had to kind of give explicit formulas for, I think these ones that end up being polynomials were the trickiest ones to track down. I know that you have done a few of those in some written homework and in iMath. I'll tell you what I did. So I don't think I'm not sharing it, but all I did was Google for finding explicit formula for sequences, and I found a half dozen examples right away. So if that's something you feel like you need more practice with, there are examples out there to be done. In fact, the one we just looked at, I found it and didn't find the answer. So there are lots of things you can work through without kind of knowing what the finish line is that are good practice. But really, to kind of recap this example, organizing it, I mean, we checked for geometric sequence first because those are easy. We understand those really well. But these quadratic ones are a little hard to figure out because yeah, you have to figure out what these coefficients are. All right.
Thank you.
Yeah, no problem. I am going to go to Rodolfo's question. He had a question about ratio tests.
Yeah,
Rodolfo,
can you do sorry. Can you do
go
one
ahead.
with like a good amount of polynomials? I guess to like the squared, a quadratic one, because there was that iMath last week, I believe. That one gave me some difficulty.
Okay, they were like quadratic sequences?
Yeah, it was like fractions, like
Okay.
a quadratic divided by another quadratic, you know, with the n.
Oh, I see what you're saying. Okay. Let me see if there's anything in that. I think towards the end of that image that he posted on Canvas. Let's look at 49. I think 49 might be a little simple. Now let's look at 49. So we're looking at the series as k goes from 1 to infinity of -2 to the k plus 1 over k squared. And, oh no, this is just simple ratio test. I wouldn't look at a power series. So again, I'm just gonna go Google, find interval of convergence ratio test. And one more thing, in general, while I'm finding a good example here, there's a page or a Paul's online math notes that there are for any topic you can think of in calculus. There's all kinds of examples you can look at. So I'm just going to pick one from this page I found. Alondra had a really good question I'm going to talk about next, because I think that is a valuable skill to look at. So series -1 to the n times n over 4n times x plus 3 power. All right, so I want to figure out the interval of convergence for this series. So how do I start doing that?
Well, you can start making the n's n plus ones.
Okay, so you said n plus 1. What process are you looking at there?
You're gonna make like two functions, I believe, and next you're gonna cross out like the ones that are 1 plus more, I believe.
Okay, so do you know the name of that thing that you're describing right now?
I don't remember it. Sorry.
That's the ratio test. Basically, just to kind of recap why the ratio test is something valuable to do. Basically, we're looking at a limit here. So let me make that even more clear. I'm looking at the limit as n gets very big of one term, of the ratio of one term to the previous term. And if I can get this thing, basically, if I can make this look like a geometric series, then I can have a better idea of when it's going to converge. So since I'm trying to treat this like a geometric series, what does it make sense for its limit to be less than?
1.
1. So geometric series converges if that ratio is less than 1. So I'm going to do the same thing here. And now I'll start, now I can start filling in those. So a sub n plus 1 is going to be -1 to the n plus 1 times n plus 1 over 4 to the n plus 1 times 1 over a to a sub n. Oh, I left off the x, didn't I? X plus 3 to the n plus 1. Now I can do all the reciprocal.
Why?
What did I
Yeah.
I messed something up. Looks like a lot of things. Is that better?
Yeah.
I think so.
All right. Now what?
Well, you could start canceling out some of the terms.
Yep. So I'm going to have -1 in the numerator. I'm going to have 4 in the denominator. I'm going to have x plus 3, an extra one in the numerator. So let's clean this up a little bit. So n plus 1 over n, and then over 4n, right? Times x plus 3. Are we okay with that? All right, now what do I do from here?
You can solve for x to see what the radius of values of x that would let it be less than 1 would be.
That might be jumping the gun a little bit.
You can do the limit
Take-
test with
Yeah,
plus
so-
1 over 4n.
And one thing I'll point out about the limit here, I care about the limit as what variable grows.
And
N. So essentially, for what I'm doing, x plus 3 is a constant. I'm really only looking at the limit as a response to the behavior of n. So as n gets really large, what is the limit of that n plus 1 over 4n?
Would it be 0? Will approach 0?
I do not believe it'll approach 0.
I
Matthew
think
Kwan
it's
says
1/4.
I got 1/4. Right, so this is one of those things. I have a rational function here. So you can compare the degree in the numerator to the degree in the denominator. And since they're equal, basically, as n gets really big, that 1 in the numerator is going to get overwhelmed. So basically, this is going to approach n over 4n. So basically what I have is this. I have the absolute value of x plus 3 times 1/4. And I want to control this. I want to make this less than 1. So I'm almost to my interval of convergence. What else do I have to do?
Plug in a value of x.
I don't think I need to plug in a value of x. I think I can actually solve to get an interval for x.
I always have to do this as two separate +1 and -1 with the absolute value. I imagine eventually you can do them both in your head, but I always have to break them out.
Right, and that's fine. I mean, I think that's a good idea, but before I do that, I'm going to do this. I can do the absolute value of x plus 3 is less than 4, right?
Oh, yeah.
Basically just multiply both sides by 4. And then from here, yeah, you're totally right. Do -4 is less than x plus 3, which is less than 4. And then I should get -7 is less than x, which is less than 1. Are we done?
You have to test both -7 and 1.
Right. So here's what I know so far. I know that everything that's strictly between, every x value that is strictly between -7 and 1, that my original series will converge. So now it remains for me to figure out what happens when x is equal to those values. So I just need to test them. So when x is equal to -7, I have this series. N from 1 to infinity of -1 to the n times n over 4 to the n times -4 to the n. So what should I do with this thing?
The 4 to the n's will cancel out. With the negative, the negative's going to affect the alternation, but that shouldn't matter.
Yeah, so I'll take this a little slower, but that is essentially what's going to happen. I'm going to combine -1 to the n times -4 to the n, and that'll become 4 to the n times n over 4 to the n. And then those will nicely cancel. So I have the limit, or sorry, I have the series of 1 over n. Do I know what this thing does?
It does not converge.
Does not.
Or
Why? What? By what justification?
is this a harmonic series?
It's the harmonic series, which is a very specific instance of what test?
Limit comparison.
Not limit comparison. I mean, you
Direct
could do
comparison?
that, but there's something a little more direct you could do.
P-series.
This is P-series. Yeah. I mean, a P-series is by definition 1 over n raised to a power. And this is that boundary case. I know that with P equals 1, your series diverges. So that's good. We're good for x equals -7. So now we'll do x equals 1.
I have a question. If the 4 to the n's canceled, why were we left with 1 over n? Shouldn't we have been left with n?
I think the question was, how will we not get n?
Yeah, because the 4 to the n's canceled.
Oh,
and
yeah.
then- Okay, I agree.
That's my mistake. Okay.
Oh, it's crossed. Yeah.
Can I still say that this diverges?
Yes.
Yeah, that'll certainly diverge, right?
Yeah.
All right. Yeah, thank you for that. It's a good catch. Okay, so for this next one, so n goes from -1 to, or 1 to infinity, -1 to the n times n over 4 to the n, and then this will be +4 to the n. So this one will eventually give us this -1 to the n times n. What does this do?
Still
Diverge.
diverges.
Diverges, right? So what is my true interval of convergence?
Just the range without the endpoints.
Yep. So yeah, neither endpoint got included. And back to why did I put 1 over n? I am so used to these things yielding the harmonic series that I just assumed it was going to, and I wasn't careful enough.
I have one more question about when doing the ratio test.
Yep.
This one was more of an ideal situation, I guess, but sometimes there's, I guess, like n squared. And next when you do parentheses n plus 1 squared, I feel like those are a bit tougher.
Can you give me an example?
So just like, when you put like n plus 1, so like when it's just n squared, let's say it's the numerator. So
Okay.
when
So
you
if I
plug
had
in that-
if I had like n squared in the numerator instead of just n.
yeah, because that will make the n like n plus 1. And next, when you would try to cancel out, you'd have like n plus 1 squared over n squared. I'm not
Okay,
sure how to go over about that.
Yeah, that's a really good question, and let's talk about that quickly. So ratio test. Is going to give me -1 to the n plus 1 times n plus 1 squared over 4 to the n plus 1. All right, so a lot of things are going to cancel out again. But the thing that you are asking me about is this. So I'm going to have a -1 up here. And for right now, I am not going to expand that. So is this the sort of situation you were looking at?
Yeah.
Okay. So from here, I'll open it up to all of you. How would we handle this?
I know we could also like factorial out n+1 if
Okay.
that's possible. I know
We
some
can go
people
ahead and
do
do
that.
that. One more thing I'm going to do, since that I'm dealing with absolute values, I'm just going to ignore the -1 for the rest of these calculations. So this will be n squared plus 2n plus 1 times x all over 4n squared. All right. What's the limit of that? And one more thing I'll do. I'm going to pull the x to the outside.
Would it be 1/4 again?
It's still 1/4 because, and even though now we have quadratics, this is a polynomial, or this is a rational function. So you have polynomial in the numerator, polynomial in the denominator. So it's really all about comparing the degrees. The degrees are equal. So really it's just going to be the ratio of the leading terms. Would that be true if the power on n was any constant?
No.
Well, 0 is a constant, which is going to throw a monkey wrench.
Okay, any positive constant, good call. In this case, it would not matter what that positive constant is.
Yeah.
Because, basically your numerator is going to be, so your numerator is obviously going to be more complicated. It's going to have more terms. But the leading term is going to be n to the p. And then the denominator is going to be 4 times n to the p. So no matter what power I use there, I'm going to have that power be the degree of both numerator and denominator. So if you're not convinced, I'll let you try out a few different exponents there. But if you kind of follow this example here, you will never get a limit other than 1/4. All right, we only have a couple minutes left. The last thing I want to talk about, Alondra brought up was, how do you look at the problems and tell which test you'll be using? I think that's a really good thing to kind of practice, and I'll get you started on, how you can, get like a flow chart in your mind. But if you haven't already, I think looking at this this image of this textbook on Canvas, pretty sure everything from like 22 to 42, at least the ones that you're actually responsible for, at a very minimum, go through those and understand what test you would use. So just kind of revisiting from earlier, what's the first thing that I think is a good idea to look at?
Divergence test.
Divergence test is a great first move. So definitely do that. What else? So let's say the divergence test does not give you a conclusion.
If
What else
it's
can
a
you do?
rational function, then, but it, what happens when you got something that's a rational function, but that's my thing, that where you've got multiple tests that you might apply to one of them and they all give you the same answer, how do you know which one is going to be the golden master that you should be answering?
So I'll give you a couple different answers. If multiple tests work for a certain sequence or series, then that's fine. Use whichever one you prefer. I think one thing that you have seen on quizzes is, and at least one recitation quiz that I've written is, what is the first, basically here's options A through E. What's the first one of these that gives you a conclusion? Because like you said, there are lots of ways to, sometimes you can have a sequence or series that, you can attack it from multiple different angles. But just to kind of start cataloging these things, you have divergence theorem. What other tests do we have?
P series, geometric series.
So P series. What does a series look like if you're gonna apply that to it?
Anything that's smaller than the harmonic series.
I think I need a little more
Where
generality than that. So what is? I'm sorry, I cut you off again.
Yeah, where the exponent is less than 1 unless you start bringing the alternating P series.
What exponent? So it sounds to me like you're assuming a structure, but that's what I'm looking for.
Yeah, 1 over n to the n to the P.
Right. So that's one good thing. If you're looking at a series that is 1 over some rational function, some one term rational function like that, that's usually a dead giveaway you're gonna be using P series. I have 1252, so what I'm gonna do is this. I am going to anybody who wants to go, you're free to go. I'll stay behind and answer questions for a few more minutes if you'd like to stay on. Otherwise, I'll let you know when this recording is live, and then I'll send out these notes as well. There is no quiz or assignment today. I have a log of who showed up and who participated, or of who was here. So you'll get credit if you're here.
By the way, Stephen, do you have any more examples of your notes? I like how you write these. So I don't know if you have other ones that are similar.
I do have solutions from last semester for the thing that's on Canvas. If you want, I can send out my solutions that I wrote to these last semester. I would just really encourage you not to look at them until you've tried these things on your own.
Yeah, of course.
Okay, but yeah, I can send those out as well.
I agree. You write these things out very clearly.
Thank you.
I have a question.
Go ahead, Jose.
It was about the ratio test. If you can scroll up, I was just confused about a certain part. Where it was n plus 1 divided by n. I thought that would mean that we have one more n on top. Can you explain why?
Not the case. So, in fact, let's unpack that a little more. So, let's say I just have a sequence a sub n equals n plus 1 over n. What would the first few terms of this look like? What would the first term be?
2.
2, and then what?
3 over 2.
Yeah, and I'll write it as fractions just to make it even more clear. 3 over 2, 4 over 3, 5 over 4, and so on, right? So the way you phrase this was you would think that this looks like you have one more n on top.
Yes.
What do you mean by that?
Where we canceled them out, where n plus 1 was on top and there was an n at the bottom, you wrote that there was n plus 1 at the top after you canceled them out.
I don't think I canceled them. Let me make sure. If I did, that was an error.
That's okay. I thought you canceled them out. Sorry.
No, yeah, that's okay. Oh no, they wouldn't cancel.
But in certain circumstances, if you let n get ridiculously large, then that a to the n essentially becomes 1. The limit of this
Yeah.
sequence is 1.
And that's what I was highlighting here. Let's pick another term out in this, let's say 100,000 over 99,999. Because that would be a term in the sequence, right?
Yep.
Yep. So, I mean, as n gets very, very large, this is going to get closer and closer to 1. And it's really all about the respective degrees, the respective powers on n. In fact, if I want to do a little bit of algebra here, I could divide through by n and get this 1 plus 1 over n. Clearly, 1's a constant. No matter what n does, this will be 1. What will this do as n gets very large?
Converge to 0.
Yeah, it goes to 0, right? So no matter which way you look at it, you have a sequence that's going to converge to 1.
Okay, that makes sense. Thank you.
No problem.
I have a quick question towards the bottom.
Okay.
So let's just say the polynomial for the ratio test, it was a little bit higher. Yeah, it was n cubed over 4n squared.
Mm-hmm.
That would go to infinity, and then
Yeah,
the
that
rule
would-
would be
yeah,
negative
mhm.
infinity. Okay, awesome.
Right.
Thank you.
No problem.